and me. All right. Okay, I'm going to talk about a subject, multiscaling and randomly forced hydrodynamical equations. I'd like to start with acknowledgements, support from these agencies. And this is in two parts. I've been interested in this in the past. So my old collaborators are given here, and this is some more recent work that we have started. So you can see Uriel is in both, and I'm very sorry to report that Ferdinand Ayo is no more now. I wish he were here. Okay, some historical perspective and motivation. Direct numerical simulations of turbulence in hydrodynamical equations indicate that turbulence with spatial power law forcing, I'll define that clearly in a few minutes, has at least two different regimes. It depends on the power law forcing, one with scale invariant statistics and one with multifractal statistics. So one of the goals is to study this in a variety of models. Here is a question for which I don't have the answer. I hope the mathematicians will have an answer, and I will come back to this question again at the end of my talk. Can these be studied by using some variant of the series of spontaneous stochasticity, rough paths, or regularity structures, some of which has been done in the case of the Kardar-Parisi-Zhang equation? And then I will go quickly over, there's a long tradition in fluid dynamics of including a driving force in the equations, and we will look at the case where the driving force is random. So as far as Uriel and I can tell, the earliest paper we could find which had a random forcing was by Sam Edwards, who looked at the Navier-Stokes equation with a random forcing term. The type will become clear as we go along. At the time of Edwards's proposal, the renormalization group was not available. But when it did become available, and after the work of Martin Sijier and Rose, and even earlier the work of Henry William Wilde, Forster, Nelson, and Stephen wrote a very important paper where they applied dynamic renormalization group methods to the randomly forced Navier-Stokes equation, and also the randomly forced Burgers equation. But the statistics that they used for the force was not enough to come near enough to what we think is homogeneous isotropic turbulence. This was first done by De Dominicis and Martin in this very important paper in 1979. And they realized that a specific form of the forcing, which I will define in a few slides, actually led at some level to what we know as K41 scaling for the energy spectrum. Subsequently, there were many renormalization group and related studies that clarified these ideas. And I list some of them here. The literature is so huge that I won't try to cover it. You've already heard the paper by Fournier and Frisch, who looked at turbulence in d dimensions. There were the renormalization group studies, Yahut and Orsag, and Joyanta Bhattacharjee also, whose talk you heard on the second day of this meeting. There was an ON model for Navier-Stokes by Moe and Weichmann, and then there was this big book which summarized the work of this very important school in Russia. Later, there was a need to see whether you could go beyond these perturbative or normalization group studies, and many years ago, some of my students and I, we looked at the randomly forced Navier-Stokes equation numerically and found multiscaling there. And much of the rest of the talk will have to do with such multiscaling in these equations. All right. So what is this equation that we are talking about? It's the good old Navier-Stokes equation that we have seen in many talks. It's incompressible. U is the velocity, P is the pressure, and U the kinematic viscosity. But this force, F, is a random force, zero mean, Gaussian, white in time, but it is power law, and that is expressed more clearly by giving this covariance in Fourier space. There's some amplitude. Then it's important here, k, the wave number, to the power 4 minus d minus y. D is the spatial dimension, y is control parameter. This Pij is a transverse projector that makes enforces incompressibility, and these are just delta functions, right? Now, the studies initially, at least, were all one-loop normalization group studies. If you don't know one loop, don't worry. It's just some jargon from field theory. I will refer to these as 3D, 3 dimensions, RF NSC, randomly forced Navier-Stokes equation. And they predicted that the energy spectrum Ek would go as k to the 1 minus 2y over 3. And you will see that if I put y equal to 4, I'll get the celebrated k to the minus 5/3 spectrum when y is 4. So this was the insight, I think, of de Dominicis and Martin. And then, of course, there was a lot of work, Yahort and Orsak, joined to Bhattacharjee, the Russian school, and so on, in too many to name. Now, once the dust settled and people started looking at these equations in detail, then it became clear that, strictly speaking, and I will come back to this point later, the 3D randomly forced Navier-Stokes equation is not in the same universality class as the 3D Navier-Stokes equation, that sort of turbulence, because of log corrections that have to do, that appear in the energy flux because of this power law force. All right, but if you look at it at some rough level, after all, logs are hard to find. For y equal to 4, as we showed several years ago, at least the exponent ratios, which you would use if you did some form of extended self-similarity, were equal in both cases within error bars. So I remind you, here's a plot of zeta p scaled by zeta 2, which you obtain from the second order structure function, and that shows clear multiscaling. For y equal to 4, and it increases if you increase y equal to 6. And here I have the Schiller-Weck parameterization of these exponents. And well, I mean, you can see that if you take Schiller-Weck to the 3D Navier-Stokes, just for the point of making the figure, then it's within error bars. There you can look at PDFs also, which I won't stress at the moment. One important thing that we noticed in our early simulations was that the conventional Navier-Stokes turbulence has these well-known vorticity tubes in plots of the iso-omega isosurfaces, but these get completely shredded because of the random forcing. But even though they are shredded, at least at the level of these exponent ratios, the two models seem to have the same exponents, multiscaling exponents, so long as y is 4. In those days, we could only afford 64 cubed and a little bit of 80 cubed. But later, our friends in Rome were able to, many of them should be here in the audience, they were able to do this with much higher resolution, and in essence, confirmed that even with higher resolution, the same results followed. All right. Then similar studies were carried out for other randomly forced models, and including the KPZ equation and the stochastically forced Burgers equation. So here's the celebrated KPZ paper. The essential renormalization group is contained in Forster, Nelson, and Stephen, but they applied it to growing interfaces. And then there was a paper by Chekhov and Yachort, which looked at the randomly forced Burgers equation and also looked at anomalous scaling there. Then Io and Jayaprakash looked at scaling and multiscaling in the stochastic Burgers equation, and then the chair of our session, Jeremy, Uriel, and I went back and looked at it with much higher resolution, and I will summarize the results for you as we go along. Now, meanwhile, as you all know, Martin Heirer has written a celebrated paper on mathematical aspects of the KPZ equation, and I'm hoping that my talk will encourage mathematicians like him to look at many other stochastically forced hydrodynamical equations, which are used especially in field theoretical studies of turbulence. All right, so now I get to the outline of my talk. I will quickly go over some of our recent work in this area. Some has to do with an equation called the Kuramoto-Sivashinsky equation, which some of you might know, and its relation to the KPZ equation. Then the one-dimensional stochastic Burgers equation, randomly forced Burgers MHD, and randomly forced 3D MHD if I have time. Let's see what we can cover. So you recall the case I have been trying to make is that the randomly forced 3D Navier-Stokes equation, the statistical properties of that for in this non-equilibrium statistically steady state are more or less the same as that of the deterministically forced Navier-Stokes equation in 3D. So let's look at one very simple one-dimensional deterministic partial differential equation, the Kuramoto-Sivashinsky equation. H is the height field, there's a first derivative, second derivative, fourth derivative, and so on. There's no forcing term, because if you write this in Fourier space, you will see that the forcing comes from a linear instability. Low wave number modes are unstable, high wave number modes are dissipative. Once you put in the nonlinearity, which is basically the same as the KPZ nonlinearity, then they all get scrambled and you get rich dynamical behaviors. The way this is written, the only parameter left here is the length of the system, and for large L, you do get a state which shows spatiotemporal chaos, which is reminiscent of turbulence. And I think, okay, so let me do the stochastic equation here. The natural stochastic equation here is the well-known Kardar-Parisi-Zhang equation, which all of you know well. So this is delta H by delta T. This is like the viscous term. This is the nonlinearity, and here's the noise. This is a zero mean Gaussian white noise. This was studied by Kardar-Parisi and Zhang for many reasons. And it was first suggested by Yachort and Orsag, and then looked at by various people like Io and Jayaprakash in 1D, and then also in 2D, in which I was also involved, that given the similar structure of these equations, please look at the deterministic equation and look at the stochastic equation, that their statistical properties, at least long distance, long time behaviors, should be the same in their statistically steady states. Because roughly speaking, the noise in the KPZ is basically equivalent to the dynamically generated noise in the Kuramoto-Sivashinsky equation. And indeed, numerically, there were many studies. I will tell you about a very recent numerical study that we have carried out. We means Dipankar Roy and I. The field to look at here is the height field. And if you subtract from it the height field at 0, there is some trivial term which has to do with the linear growth of the interface. And then here is gamma t to the power beta kpc. And this is what Kostya talked about. You remember he said one force, one result, and this exponent is the same no matter what the force. But what was noticed by Preyhofer and Spohn, that there is a subdominant object here called chi, and this chi is a random variable and is therefore characterized by a probability distribution function. And the important insight of Preyhofer and Spohn and many people who came after that, that this chi, the PDF that it satisfies, depends on the initial conditions. For example, if you start with a wedge initial condition for the height, you will get a Tracy-Widom distribution of the GUE type. GUE means Gaussian unitary ensemble. If you start with a flat one, then you get Tracy-Widom with Gaussian orthogonal ensemble. So this is the paper that I wrote recently with Dipankar. And our hypothesis was the following, that if we seriously believe that the statistical properties of the stochastic KPZ equation in 1D and the deterministic Kuramoto-Sivashinsky equation also in 1D, then we should be able to determine the PDFs of this chi here that I have just defined and see whether we get these different types of distributions. For the wedge initial condition, we found the T Tracy-Widom GUE. For the flat one, we found Tracy-Widom Gaussian orthogonal ensemble, right? So this is a very, very precise and sensitive test for the equivalence universality-wise of these two different models. The statistical properties of the spatio-temporally chaotic state in the Kuramoto-Sivashinsky equation seems to be within error bars the same as that of the KPZ equation. Why do I discuss this? It doesn't look immediately like a hydrodynamical equation. I do because the Kuramoto-Sivashinsky equation has often been, suggested. It has often been suggested. Probably suggestion goes back to E. Promo or even Uriel, that it's a simple model for turbulence because it generates its own spatio-temporal chaos. Okay, so now let's go to the randomly forced Burgers model. This will look more similar to the randomly forced Navier-Stokes equation that I told you. So here's Burgers, the usual terms, and here is a force. Now we will use a random force, and just like in the Navier-Stokes case, it's zero mean, Gaussian, white in time, and the covariance in Fourier space is such, delta functions, but mod k, k is the wave number to the power beta. Okay, and again, by using the same methods that were used by de Dominicus and Martin, basically contained in Forster, Nelson, and Stephen, you can carry out a one-loop renormalization group expansion. It turns out that when beta is -1, then you get a K41 type spectrum, k to the -5/3. In general, if I've got all my signs right, it's k to the -1 plus 2 beta over 3. All right? So, question, does this happen? And this, as I said, was first done by Ayo and Jayaprakash. They used the standard spectral method. And then Dhrubaditto, the chair of our session, Jeremy Beck, and Uriel Frisch, and I, we thought we can do better by going directly to the implicit limit, where, as you saw in Uriel's talk, we have this maximum principle for the velocity potential phi, which is related to u in this manner. And then by using a nice algorithm for fast Legendre transforms developed by Nules and Vergasola, we were able to study it in great detail. And I show you not data from that paper, but data that have been generated again by Dipankar Roy, who we want to do some more. but this was a validation. So this is beta equal to -1. This indeed shows, first thing, if I'm not showing you the energy spectrum here, but if you looked at the energy spectrum, this would be a -5/3 spectrum. What I'm showing you here is the log of the order p velocity structure function versus log L. And from suitable slopes and careful analysis, you can extract from it the multiscaling exponent psi p, and you can plot psi p versus p. And this is what Drovadito, Jeremy, Uriel, and I did in 2005. And we got something like the red curve. So numerically, if I look at a curve like this, I'll say, oh, that's multiscaling. But we argued at that time that this might be some very subtle effect, and actually it could be bifractal scaling in disguise. Bifractal scaling, you can argue, and I won't go through the exact details in our paper, would be the blue line. So p divided by 3 up until p equal to 3, and 1 thereafter. And this has to do with some subtleties in these randomly forced equations, because you see there is this power law in the force. And this power law in the force translates into some log corrections to various quantities, including energy fluxes and also energy spectra, which are hard to detect. So when you are trying to, numerically evaluate log-corrected power laws and subdominant terms, you can get apparent multiscaling. You believe that if you do high enough resolution, that will go away. But this is already 2 to the 20, which is much, much larger than was done in the old days by Ayo and Jayaprakash. And yet we haven't reached, numerically speaking, the bifractal thing. But in our heart of hearts, we do believe it will be bifractal. But this shows you that even for this very simple model, the numerics are very challenging. Then we looked at beta equal to -0.05, because recall that the one loop results, the normalization group results, become better and better for small beta. And so this is beta equal to -0.05. And here I show you the energy spectrum, and you can fit it in this region. And indeed, it agrees with the one loop result, which you expect for small beta. Okay, now then you can ask what happens to multiscaling. Should you get simple scaling because it's very small beta? And it turns out it's subtle. A plot of the structure functions versus L, if you have enough L, and that's why you do very large simulations. You have 2 scaling ranges. I won't go through all the details, but in one scaling range, in some range of L, it is simple scaling with the simple exponent given by the one loop theory. But in the other region, it is multiscaling. Multiscaling modulo all the caveats I mentioned are probably bifractal. So, excuse me. So what's happening? Our best guess at the moment is that the way the multiscaling region increases as we increase beta is that this region expands and this region contracts. And that's how we go from simple scaling to multiscaling as we increase beta. Okay? And multiscaling, of course, could just be bifractal in disguise. All right. So I still have about 10 minutes to write it though, or slightly more. Hello? Hello?
It's actually longer. You have 10 minutes.
Okay, I have 10 minutes. Fine. I won't trouble you with too many details. Okay. And then you can say, well, I mean, Can we do better? I mean, can we look at more complicated models? After all, hydrodynamics doesn't stop with just Navier-Stokes. We all know about MHD. But there's a set of equations which is not as well known as they should be, which is a Burgers analog of MHD. This was first written down by Thomas and then by Fleischer and Pat Diamond. And my favorite paper on this subject is by Abhik Basu, a former student of mine, Jayanta Bhattacharjee and Sriram Ramaswamy. So here are the equations. Please don't look at the details, but believe me, this is a Burgers version of MHD. U is the velocity field, B is the magnetic field, mu is the kinematic viscosity, mu is the magnetic diffusivity. Their ratio will give you a magnetic Prandtl number. And then you have these forcing terms in both the velocity and the magnetic field equations. Now, you can also, those of you who do MHD know that often we use Elzessa variables, which are the sums and differences of the U's and the B's. And then these Nu's are sums and differences of the viscosity and magnetic diffusivity, etc. So you can define a magnetic Prandtl number, etc., etc. They have various nice properties, which I will not stress. But you can again use this simple model for testing statistical theories of MHD turbulence, which I will get to presently, which are exactly the way we did earlier for the other models. Again, we are going to look at randomly forced equations. So here are the force statistics, again, k to the beta, mod k to the beta, and no cross correlation between these two. All right. And this is still in 1D, so I don't need to put in transverse projectors. All right. And here I'll give you data only for -1, beta equal to -1, which is the value which will give the Kolmogorov -5/3 spectrum. So this is the paper which I mentioned already by Basu, Bhattacharjee, and Ramaswamy, which actually did a one-loop perturbative RG for this. And they showed, in fact, that for beta equal to -1, you get the K41 energy spectrum for the same reasons that the earlier studies got it for this reason. Basically, in D dimensions, if you have K to the -D in the noise, that's it. That gives you, at the one-loop level, -5/3. So we can study it by some pseudospectral methods and clever coding using CUDA, Fortran, GPU clusters. So we can, and one thing this allows us to do is to explore a large range of Prandtl numbers, which have not been studied in any of the field theories. So field theory basically doesn't look at that control parameter at all. In his talk, Alexei also mentioned quasi-Lagrangian fields without defining them. So since we will use them occasionally, I will define them once for you. For any field phi, the quasi-Lagrangian field at the point x in t is the Eulerian field at x plus r and t, where little r is the position of a tracer particle which was at some position r0 in the beginning. All right? And these sorts of fields, as far as I know, were first suggested by Beliniker and Lvov, and they're important in removing what are called sweeping effects. Sweeping effects basically what goes into the Taylor hypothesis. So any spatial separation delta x is related to delta t by some mean flow velocity. In a pseudospectral simulation, that could be the mean velocity of the largest eddies or small k modes. All right. We have many simulation parameters. I will not bore you with those. I will show you how, if these are the initial velocity and magnetic fields, velocity is red, magnetic field is blue, then you can see these structures evolve, and there are these, jumps, etc., which are like, expected in Burgers, and this is how it evolves. So this is the statistically steady state which we will examine. and we can get energy spectra. And for the statistically, stochastically forced model, indeed, we get minus 5/3, which is what we expect from the theory, this one loop theory that I mentioned. But what about multiscaling? So you can define the structure functions in the usual way, some difference of fields raised to the power p, angular brackets mean, average over the statistically steady state in the inertial range. And then if you do it, again, like we had in our randomly forced Burgers model, you can't see this very clearly perhaps, but the red data points are for U, so blue is for B, and the other colors are for Z plus and Z minus, the others are variables. And basically the same story for all Prandtl numbers within error bars. I mean, okay, you can say that there's some difference. But again, for the same reasons that we argued in the simple randomly forced Burgers case, most probably it will be just simple bifractal scaling. But, I'm showing you the numerical results without disguising anything. Probably we need to go to huge system sizes. This is already 2 to the 20 collocation points, or points, excuse me. This is a pseudospectral. You can ask about time-dependent structure functions. It is late in the day, and these are rather technical things. We sorted these out following suggestions of Lvov, Pudivilov, and Procaccia, and then we did various models with Shamridhi Shankar Rai and Varitva Mitra. I think Prasad Perlekar was also involved in one of these. So ignore this for the time being, but just like we have, we have increments, and then we take differences of increments, but when you do time-dependent structure functions, you have to make these time-dependent also. And when the dust settles from it, you can extract time-dependent structure functions which decay in time. How much they decay in time and how rapidly depends on the, order P and so on. And from these structure functions, you can extract times. For example, you can extract an integral scale time, which you take a suitable moment of the structure function and raise it to the 1 by m power. You have to normalize it by the time-independent one. And then you have a dynamic scaling ansatz, which is basically, don't look at the details. It says time is a function of r, is r to some power, and this is what was done in critical dynamics and critical phenomena, and that power is known as the dynamic exponent. Here we have dynamic multiscaling exponents, and by using arguments which I will not go through now, such linear bridge relations between these dynamic exponents and equal time exponents were first discussed by Procaccia, Lvov, and Pudivilov, and then we discussed many of them for different types of ways of extracting times. And here is a linear relation between the time, the exponent for the time, and the equal time exponents, which we have already talked about. Okay, then you can get them from suitable log-log plots. So I'm going to plot these exponents for the time dependence versus the order P. If it were bifractal, the answer would be this blue firm line. But our numerics indicates this line, and that dashed line is the result that we would have got from that linear bridge relation. So the bridge relation seems to hold reasonably well, but again, like for the equal time exponents, the data are not good enough to show what would be the result if it were bifractal scale. Okay. All right. So now, okay, you can do this function of Prandtl number, which I won't do. Now, in the last few minutes, I will say that, of course, you can do full randomly forced MHD turbulence. This was not done until recently, although much of it was done by Ganapati Sahu in his thesis. It took us, quite some time to put it in nice form. So again, to make a long story short, here's full MHD with random forcing, incompressible, divergence v equal to 0, of course, and the same sort of forcing, k to the -3. Okay, so it's like beta equal to -3, and these are the transverse projectors, etc. You can do it. It's again, the field theories exist. They're nicely summarized in this old review by Mahendra Verma and other people who have used the field theory methods that I told you about. There's a whole bunch of papers. And again, the field theory for first approximation is typically one loop field theory, which gives a simple sort of scaling result for the spectrum. We can do the full numerics. And, one thing I didn't emphasize, these randomly forced models, they give you a longer inertial range because of the power law forcing. But you also need to average much more because there's a lot of this noise. You can see what the energy does as a function of time and so on. Then you can ask, what is the spectrum doing? So I give you a sort of compensated spectra also. Strictly speaking, data could be consistent with a -5/3 or -3/2. I think -5/3 might be slightly better, but with this sort of resolution, our highest I think is 512 cubed, if I'm not mistaken, and so on. We have carried out a careful. I mean, I won't show you all the spectra. You can look at the dissipation spectrum to see that you're well resolved, pressure spectra, and so on. Again, I want to make a statement about plots of isosurfaces of the vorticity, current density, etc. Just like we had found in the three-dimensional randomly forced Navier-Stokes equation, vorticity tubes or current tubes, they all break down. They become completely disordered. And yet, at least at the level of extended self-similarity, exponent ratios seem to be the same. So theories that build upon, excuse me, getting exponents out of the codimensions of the most singular structure, I don't know whether they're correct or not. You can look at PDFs of velocity and magnetic field increments, etc. I won't worry you with this, but we can measure structure functions in great detail, and we can make these types of plots of structure functions versus order P, and they are not very sensitively dependent on Prandtl number. We have also carried out a detailed comparison with conventionally forced MHD, and these exponents are within error bars. So as far as multiscaling exponent ratios go, the randomly forced models are, nearly the same as the conventionally forced models. You can look at hyperflatness. I won't worry you with that. So here's a quick summary that equal time exponent ratios indicate slightly more intermittent P than U. But even though the isosurfaces are shredded up by the random forcing, the exponent ratios seem to be the same. So there is some, okay, I mean, it tells you how far you can go with these models. So I end with what I began with, that direct numerical simulations of these randomly forced models seem to indicate that with a certain parameter, the y that I told you about in the power law forcing for small values of y, you will have scale invariant statistics. As y increases, the scale invariance will be broken insofar as things will be multifractal. So again, there are subtleties with log corrections. There are subtleties in the field theory that at y equal to 4 in the three-dimensional equations, not only is the small parameter y no longer small, and infinity of marginal operators come into play at y equal to 4, and they all become relevant at y greater than 4, so simple renormalization group methods don't work very well. In addition, there is the sweeping effect, and if you are serious about removing the sweeping effect, you have to perhaps go to a quasi-Lagrangian description or extract subdominant terms from conventional Eulerian treatments. Given the rich structure of these randomly forced equations, the turbulence in them, I think, at least from my point of view, I would be very happy if mathematicians could look at such models and make them legal in the sense that Heirer has made KPZ legal, and to see whether the sorts of inequalities that John Gibbon and Charlie Doering, etc., write down, whether they can be obtained for these stochastic PDEs. And as I have tried to show you, there is a long tradition in fluid dynamics of studying such random driving forces, and I would like to invite all of you to take part in these studies. With that, I thank you for your attention. I'll be happy to answer any questions that you have.
Thanks, Rahul. Charlie Doering already made the comment.
Mm-hmm.
Say again what you intend to say.
Yeah, I can just ask it.
Somewhere
Sure.
there is no noise coming.
So Rahul,
Yeah. Mm-hmm.
so there's randomness, but then there's also the fact that you're considering forcing spectra that have that are not narrow band, right? That are extending down to small scales.
Sure.
And so I sort of asked this as a question, then I looked up a paper while you were talking and reminded myself that already, I don't think you mentioned this, already in the early 2000s, Luca Bifarale and his collaborators did a lot of DNS, or not DNS, but simulations with white noise, but power law forcing.
Yeah. I mentioned that paper.
Oh, you did? Okay.
Yeah.
Okay, good. And they found basically what you had, I think. Once the once the forcing sort of doesn't correspond to being in L2 anymore, that it has a fatter tail in spectrum, then you get this significant difference in the small scale structure. Now, I would also, so one question is it randomness, or is it just, is randomness essential there, or is it just the fact that you're doing small scale forcing? For example, you play that trick where you have the forcing function be a function of velocity to make sure that you always, that the forcing is always stirring the fluid appropriately, but then you rescale the amplitudes. And I'll say one other thing. Remember also that if the forcing function, at least for non-stochastic, is not at least in H-1, which means if it's too rough, then we don't even have weak solutions for 3D Navier-Stokes. And I just want to remind people of that. So some formal thing about forcing it with really strongly at small scales has a problem, for 3D Navier-Stokes. But any comments on all these things?
Sure. First comment is, in the numerics, of course, we cut it off at some K.
Well, of course.
Okay. Then in the reason for making it random is that when the field theorists get into the game, to use the Martin-Sigier-Rose machinery, if you want to do it, they need it, right?
Yeah.
I mean, you could, of course, do it in some other way. I think
Right.
Mahendra probably had a comment. I mean, you could do it some other way, but strictly speaking, the way the field theories are set up, you need the noise there in this way. So then the question was, these field theories get these one loop results or whatever, but is there multi-scaling in those models? And that was the first question we addressed, and we did it with very low resolution, and then about 6 or 7 years later, Luca and his group did it in much greater detail. So that was probably okay. But they also have a cutoff, and then, okay, then I've tried to give you the most honest answer to what the numerics
Sure,
is.
sure.
Yeah. About the the force power law, exactly. So that's why I would like the mathematicians to look at it and tell us what is legal and what is illegal mathematically. Right? So, yeah. Okay.
Nick, I would ask Mahendra Verma to say his comment, but before that, I think Greg Ink said something which is relevant to what we are discussing now. So, Greg, please go ahead.
Actually, I mean, I was just saying relevant to Charlie's comment, there was this constrained Euler system. I think maybe this was one of the things Charlie had in mind, was the constrained Euler system considered by Shea and Jackson, where it's this application of the Gauss principle of least constraint, where you add a deterministic forcing to make the spectrum whatever you want. You can enforce any power law you want at all. And it probably has similar properties as, I mean, again, maybe harder to study with field theory methods, but has similar properties as the random forcing, presumably. In fact, this actually led me into my next question. Thanks, Charlie, which was that one of the things that Shea and Jackson found, I don't know if they ever published it, was that if you consider the analog of Y in their case, and now it's just directly related to the energy spectrum that they impose, what they found is that intermittency corrections seem to appear at Y equals 3. And I wanted to ask you about your, of course, this was related to the conjecture of De Dominicis and Martin, that there would be this crossover. So I was just wondering, what is your current view on that?
Well, I mean, I think if you are asking a Navier-Stokes or MHD question, we need to do much more careful study.
So you just
In
don't think...
the case of Burgers, I showed you the best we have. So it seems it's not suddenly multiscaling. You see, I showed you the data for beta equal to minus 0.05. There is a region which is simple scaling. There is another region with multi-scaling. So as you increase beta in magnitude and take it closer and closer to -1, which will give you the Kolmogorov spectrum, one scaling region slowly ousts the other. Okay.
So there's no abrupt transition where it suddenly...
Doesn't seem to be. I mean, at least in the randomly forced Burgers. But there also we are pushing the numerics and looking at the details. And then, of course, there is the added complication in Burgers that in spite of all our high resolution, we are still not sure whether it's multi-scaling or bifractal. Because that's an added complication, but that's a separate issue.
Okay. The numerics is hard.
Yeah, I mean, if you do it carefully, I mean, you can do it sloppily, of course. Right? Yeah.
Yes. Okay, thank you.
Okay, Mahendra, would you like to say something?
So I'll make two remarks. Well, question and remarks. So this Mecom's work is self-consistent field theory, and I particularly like this procedure. And the reason being, I'll tell you. So in fact, Uriel and Pouquet and so on, they have field theory for MHD.
Yes,
but unfortunately, it could not be closed. I mean, Uriel can comment on that with Jacob-Zog, because it's just too complicated. There's too many forcing, too many with parameters. So with Jacob or with Mecom, I could manage to get the MHD work done because it was self-consistent, less parameters, and they are as good in terms of predictions. Like Kolmogorov constant, you can compute that, and it's very good.
Yeah, so that I guess is sort of like a closure of some sort. Which
it's not a closure, it's a full-fledged RG, but it assumes, it does RG step by step, but it doesn't really assume forcing. but it's self-consistent like what you do in condensed matter physics, like random phase approximation.
Yeah, that's a closure, no?
So it is in fact pretty formal.
No, I know. I've looked at those papers, but okay. I mean, I was just trying to make connection with the standard field theory.
No, I didn't mean. I just wanted to inform.
Sure, sure. No, I know that. I know that. In fact, I know your paper also. Which
and second thing is thermal convection, which is, I mean, here the forcing comes from temperature, buoyancy.
Yeah, of course, of course.
Now there it is pretty nice that we still get phi-3rd, but you can compute at least numerically. JKB has done some work for field theory as well. But if you do it numerically, then the spectrum is pretty steep for forcing. We find it to be phi-3rd, but that's coincidental for Prandtl 1. For Prandtl small, thermal Prandtl number, it is pretty steep. And that's the reason why Kolmogorov pops up for thermal convection as well. So this, I mean, in places where forcing is at all scales like buoyancy, or MHD itself is the forcing at all scales, right? That J cross B is everywhere. I think it's real to have forcing at all scales. Rotation has forcing at all scales. So I think it's real. I mean, it's not Kolmogorov having only large scale forcing. It's a pretty idealized case. Forcing in.
Yeah, it could be, but I'm not an expert on convection. But I mean, I'm sure people like Charlie can answer this. But of course, it is. But in any experiment, things are bounded. But how large scale it can be, we'll have to respect the mathematics, I guess. But I'm not an expert, so if Charlie can address this question, it would help.
Well, I would just say, I mean, the forcing is not independent there. The forcing is tied in with the flow, which is tied, it's, I don't think you can just, break it apart and say convection has a, anyway, that's my feeling about that. It's all connected. It's all one.
So, well, convection has this temperature dependent force, theta z cap. So that is, and it is all scales. So you can do Fourier transform, and you did this very carefully.
Sure. But that's an output. That's not an input.
No, it is input.
That's not an input to the problem.
It is input to the Navier-Stokes.
But the Navier-Stokes equation feeds back into the temperature equation.
It's coupled.
Yes, it's coupled.
You see, it's not like you put that forcing on there. The forcing emerges. It emerges.
I mean, this way it's useful to think of it in Grashof terms, as John Gibbons said the other day. That's the external control. Okay.
I believe it is. It's really connected to this. So in fact, we did quite a bit of connection with that. So I'll send you the paper.
Sure. Thank you.
Thanks,
So,
Mohan.
thank you.
Meanwhile, actually, Alessandra and Greg were having a conversation about some of Alessandra's old results.
Yes.
Like to
Can Alessandra tell us?
No, just there was a comment about the presence of intermittency at a given y exponent. I'm using the same notation that you were using, Rahul, in your talk.
Yes.
And so I said that our 3D data for Navier-Stokes show that we had for y equal 3.5, we have very small or no detectable intermittent corrections, in the sense that the PDF of the velocity increments at different scales could fall one onto the others, except for the left tail, which had some asymmetry. And then, so at that exponent, in that case, we said that intermittent corrections were almost disappearing. Those runs were not at very high resolutions. Now we could run at much higher if we
would, but right.
It was just this.
Thank you for answering that question. Thank you. Right.
Anybody else?
I have one small comment, actually, not as technical as the lectures have been. One thing I like very much in the project, your program, is moving from Burgers to Kuramoto-Sivashinsky for the following reason. I'm not really a stochastic person, I'm more deterministic. But we know that Burgers deterministic with forcing always have a trivial attractor, which is one steady state. While Kuramoto-Sivashinsky deterministic has chaotic motion, so it's closer to turbulence than Burgers. And I hope by moving into the MHD Burger-like, that one can probably see that there is some kind of like, even a deterministic level with forcing, that one can see some chaotic dynamic. I don't know, this is subject, maybe one should really investigate that to see if there is chaotic dynamic. Maybe numerical simulations can indicate that. This is my only comment, because there was some versions of what's called Burger-Sivashinsky, namely adding to the left-hand side minus U term, like in Burgers, to show the instability at the low scale. However, this equation also have trivial attractor, namely goes to steady state eventually. So in that sense, it is not the natural generalization of Burger to mimic instabilities and to mimic chaotic dynamics. So I think moving to Kuramoto-Sivashinsky or to the coupled MHD Burgers equation is a good idea. That's my only comment.
Thank you very much. We will look into that in detail.
A good idea, indeed.
Yes.
Anyone else?
Yeah, may I ask a question?
Sure.
So I'm not from fluid dynamics background, so I don't have much idea about this. I have a rather naive question about, so I saw a lot of nice scalings coming out from the theory, but these are for 1D burgers in a periodic domain. So I was wondering, like, all these painstaking analysis, how much do they prevail when we try to see, try to explain some experimental phenomena, for example, because everything happens in 3D or 2D at least. So all these scalings or all these very, very detailed data analysis, how much do they translate into nature? Maybe this is a very ill-posed question.
No, it's not an ill-posed question. It's a very good question. So, of course, as you noticed, I did study 2 3D models. And the experiments, of course, are in 3D, but with boundaries. But you saw in the very beautiful talk by the previous speaker, Bérangère, showed you how, when you look away from boundaries, you will see the same exponents that, if you have homogeneous isotropic turbulence, I mean, if you don't have residual anisotropy and so on, or if you take care to remove it by some suitable SO3 decomposition or something, you will see these exponents. These exponents are measured in wind tunnels for the 3D case. I did discuss 2 3D equations. The 1D equations are a good learning ground, testing ground. If you can't do 1D well, you can't do 3D well. There might be some subtleties in 1D which you have to look out for, but once you look out for them, then you are well prepared for 3D. Yeah, and thank you for the chair also. Thank you very much for chairing the session, Rubarit.
You are welcome.
Thank you, Rahul, for a fantastic talk. Thank you very much.
Thank you. Thank you very much.